Okay, welcome back. So we are now back with the indices. So we were looking into the hash indices. So you see, this is the idea that we have this very big table. I mean big because we allow for a lot of empty cells that has positions. And we have this magical function h that whatever you put inside gives you instantly an integer that you can use as a position in this table. So this is instant. Looking up in a table is also instant because this is something we know very well how to do in computer science. And that means that we can almost instantly get back to the object that we are looking for. All right. But there's a few limitations for hash indices. So one of them is that, as you could see, it's a bit of a random and a bit of a mess in the way that that we put the values in the positions, right? So we cannot have interval checks. We cannot say, please give me all the centuries between 5 and 10. That doesn't actually work, right? Because if you see, this is all randomly put in there. So we do not support range queries in this way. In life, also in real life, the hash function isn't as magical as we would like it to be, because it would be awesome if the hash function never collides. Like if you give two different inputs, it never gives you the same position. That's the wish list. In real life, it happens that there is a collision and two values land in the same position in the table. That's okay. We know how to deal with it. It's just going to be a little bit slower. And so what you need if you want to avoid these collisions and keep being fast is a very, very, very large table here with a lot of empty rows in order to avoid the collision. So it consumes a lot of space to actually have a hash index like that. So you see, hash indices are ultra fast, but they have a few drawbacks. This is why we have tree indices. And the idea of tree indices is that instead of having this magical function h, we organize the values nicely in what looks like a tree in computer science. And the trees are also organized in such a way that we have multiple values sitting together in a big block. And the idea is that the disks on a computer, they love what is called block access, meaning that when you read from a disk, you don't query one bit at a time, a bit and a bit and a bit, or one record at a time. You typically read in a single batch 4,000 bits from the disk. So this is why, because this index is actually sitting on disk, we like to have structures that do that. Right? So the idea here, I'm very quick because that's kind of technical for computer scientists, but basically this is a tree structure. We have the root here and then the children, you know, it just goes down. And then we have all the children here. These are called the leaves at the same depth. So you see, this is the ancestor. These are the children, and these are the grandchildren. All of these leaves here are grandchildren. This is what I mean that they are all at the same depth. All right. So typically, in a tree index like that, we have an interval of a low number of children. So we say, for example, all nodes, except of course the leaf nodes, have between 3 and 5 children. They can have 3, 4, or 5 children. For example, this node right there has 1, 2, 3, 4 children. This one has 1, 2, 3, 4 children, right? So this is between 3 and 5. The root, the ancestor, is special. It's the only one that can have less than the minimum number. It cannot have more, but it can have less. So here it's between 2 and 5 children, actually. One child doesn't make any sense, then you can just remove it. It's redundant. But between 2 and 5 for the roots. And so there are these parameters that we can adjust between 3 and 5. More generally, it's between d plus 1 and 2d plus 1, and you can pick whatever value of d you want. And typically, that value is taken in such a way that the size of that is roughly 1 block on the disk. Okay, and so the actual values of the index, so for example, the centuries that we want to have, they are at the leaves, right, all the way here. And the idea is that then when you look up something, for example, if you have here that's kind of boundary, everything that comes before is on the left, everything that comes after is on the right. In fact, it's exactly just like when you look up words in a dictionary. You basically open the dictionary in the middle, and then you see, okay, your letter P, you're looking for F, so you go to the left and so on. And then you just fine tune and fine tune and fine tune until you find your words. This is called binary search. in terms of lookup. So maybe you didn't know it, but whenever you open a dictionary, look up a word, you're doing a binary search. And so the idea is that this tree that you have right here, this is actually implementing a binary search. It's not as fast as a hash index because the hash index is, as I said, instant. This is actually called logarithmic. It means that every time you multiply by a factor of 10, you add a constant amount of time. For example, I'm just caricaturing, but every time you have 10 times more, you add 1 second. 100 times more, you add 2 seconds. 1,000 times more, you add 3 seconds. So you see the time it takes grows less than the amount of data. This is why it's called logarithmic. And so we love it in big data when we have logarithmic lookup times, right? So you see that here you have like an insane amount of values here, but you only need 3 comparisons in order to find any value in here. It's 1 comparison here, 1 comparison here, 1 comparison here, right, roughly. Okay, so one important thing to notice is that if you have a number of trees in the street, the number of intervals between the 3 is n-1. If you have 3 trees, there are 2 intervals. If you have 10 trees, there are 9 intervals. What do I mean here? I mean that if I have 3 children here, 3 children, then I have 2 comparison keys in there. If I have 5 children, 1, 2, 3, 4, 5, then I have 4 keys in there. So that means that if I tell you between 3 and 5 children, that means between 2 and 4 comparison keys in there, right? Again, what are these keys for? They are for the lookup. Because when you arrive and look up for a number, you compare it with these keys in order to find out where you're supposed to go for your lookup, right? Okay, so here's an animation, then you will understand. Now, let me build a tree, and I keep adding, in that case, the specific case of increasing integers. Of course, in real life, it's not going to be like that, but just to show you. So I start with a very trivial and simple tree that only has the value 1, there is no children, and so on. Then I keep adding 2, 3, 4, and imagine that I only allow between 3 and 5 children, meaning between 2 and 4 values. Here, I have 1 too much. I cannot have 5 values in the same node. What do? I split it, right? So in order to split it, I just put 3 here and 2 here, and then I add a parent right there, and 4 is telling me, okay, less than 4 is on the left, more than 4 is on the right. So you see here the logic of the index. Now I have 3 values in here and 2 values in here, I'm fine. Let me keep adding more. 6, 7, that's 4 values, 8, that's 1 too much. What do? I split it again. Then I need to add another value here for less than 4. Between 4 and 7 is right here, and more than 7 is right there. I keep adding 9, 10, 11. Okay, I need to split again. Then I have, 10 here. Now I have 3 values in here. That's fine. So you see between 7 and 10 is here. More than 10 is here. And then if I continue and fast forward, at some point I will arrive to that. And then if I try to add 17, then I split it. But then, okay, I propagate the problem because now I have 5 here. So I need to split again. And you see, this is how the depth of the tree keeps increasing. The more values I add and I add and I add, the more the higher the tree is going to become. Right. But it's logarithmic, meaning that it's all under control. If you have billions of values, you will have 1 level per 0 in the power of 10, if you want to simplify a bit. It's logarithmic. Okay, so let's then do it in MongoDB. So we have this collection of documents, but let's not use a hash index. Let's instead use a tree index. So it's going to be exactly in the same way. I just go document by document, object by object, and I just build my tree. So let's start here. I'm going to take a 2, 3, b plus 3, meaning that there are between 2 and 3 children. It's only because these are on slides. In practice, it's going to be like 1,000 values or 1,000 children per node, right? But you can imagine how ugly it's going to look on my slides if I show you that with 1,000 children, right? So this is why I'm just simplifying. So between 2 and 3 children, okay. So 20 pointing up here. Then I add 20, it's already there. Okay, then I add 19, you see, pointing here. Then I add -4. Oh, that's 1 too much because I have at most 3 children. That means at least 2, at most 2 values, right? So I split That's easy, right? And then I add this 20. Everything on the left is less than. Everything on the right is more than or equal. Okay, now I have -6. Okay, that's too big again, so I need to just readjust like 2 here and 2 here, right? And then I have 20 here. So you see, this is my index. Of course, here it's only 6 documents, right? And here it's very few values. But I hope it gives you the idea of how it scales to a billion different documents. So we build this structure right here, and this is our tree index. So now we have a query. Imagine we called the create index in MongoDB asking for a tree index. Now somebody arrives and says, okay, find me the centuries.
Do we have a question in the chat?
Yeah.
Blue cells are children or no?
So the blue cells are basically the leaves. Let me come back. Oh, that was a question on what is the load. What is very important is to distinguish between the notion of children and the notion of the keys in between. The idea is that here, for example, this node here has 2 children, this and this. These are 2 children, right? It's the arrows here that you see the children. And because we have 2 children, we have 1 key in the middle, right? So this is exactly what I showed earlier. Like here, you have 1, 2, 3, 4, 5 children. And that means 1, 2, 3, 4 values in between, right? Now, what about the leaves? The leaves, of course, do not have any children, right? But they still have the same constraint. It's as if they had children, right? So for example, here we have 3 values that would be 4 children. If you had children, there would be 4 of them, right? So this is the idea. So basically here, the idea is that if I have 2 values, that is as if I had 3 children, right? Does it make sense?
Yes.
Yeah,
thank you.
Awesome, perfect. So this is why we are at most 2 values, because at most 3 children. Okay, so then the query comes in. What do I do? So the query tells me I'm looking for 19. Okay, then I start here at the root. Then I compare with 19. Oh, I'm super lucky here. I'm so lucky that actually I'm on 19. But anyway, I know that I have to go on the right. Right, on the left would have been strictly less than 19. On the right is at least 19. So I go on the right. And then I find here 19. So you see, I can very efficiently find that, that leaf that corresponds to my value. And then all I need to do, just like in the hash index, I follow the pointer and I find the object. Right. Oh, sorry. I didn't notice one thing. This is a range query. It's not equals 19. It's greater than 19, right? So I don't only take the 19 here, I take everything that is on the right. So I basically take 19 and everything there. So this is why I not only follow this pointer, I also follow this, and this of 20. And this is how I find that I return this, and this. This is how, with a tree index, I can actually execute a range query, meaning century greater than or equal to 19. Okay. Is that clear how it works? In the lecture hall, yes? All right. And in Zoom, is that clear to everybody? I'm waiting for a confirmation, making sure you're following. Yes, it's clear. Awesome. And we have a question, Wenqi?
With why 19 stored in the leaf, an alternative would be have the pointer directly from the root to the object.
Yeah, you're absolutely correct. You could also design the index differently, meaning that since there is also already 19 here, you don't need to have it a second time here. It's really a matter of convention. If you have the convention that all your values must be on the leaves and then you repeat them above, that's called the B plus tree. It's called the B plus tree. If you do not repeat the values, and if you would have like eliminated the 19 here and only had it here, that's called the B tree, right? So you're absolutely correct that this is an alternate design and that exists, and that's called the B tree. Right. It works in the same way. It doesn't make a big difference. There are a few advantages of having everything on the leaves because we love symmetry and elegance in computer science. And so there is some elegance in having all of the values nicely arranged on the leaves. Right. Any other questions? Yes? Oh, do you mean because you need to compare within a node? Oh, I see what you mean. Okay, so this is actually, so let me repeat for the people on Zoom. So you asked about the worst case, like that. I told you, okay, that's logarithmic, so that's the average case, and you're asking about the worst case. You're absolutely correct that I could be out of luck and have a tree that is not very well balanced, that there could be like very little on the left and a lot of the right on the right and so on. This is a bit fixed by the requirements that all the leaves must be at the same depth. So what you cannot have is a depth of 2 on one side and 1,000 on the other side, right? But nevertheless, you could have a bit of imbalance. Oh, I see. Yeah, but in that case, I think that there is a mechanism called rebalancing. So if that happens, that you have an imbalance, then the code that maintains the structure is going to reorganize the tree in order to make it balanced again. Right? Does it make sense? Yeah. But the concept of worst case, best case, average case, and so on is actually core to the lectures on algorithms and data structures in computer science. So this is definitely it's a bit advanced, but it's definitely considered. But here you can really safely assume that in a database, in a production level database system, these indexes are going to be maintained in such a way that it's more or less balanced in there, so that you don't have these issues. Right. Okay. Another question in the chat?
No.
All right. Okay, so coming back to MongoDB, what's going to happen is that in MongoDB, I told you about this hidden field or this field that all of the objects have. If you don't have it, MongoDB will add it. It adds a field called _ID to all your objects. MongoDB will always, 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 always have a tree index on that field. What that means for you is if you look up an object by key, 2 milliseconds, instant. All right? For the other fields, that's called the secondary index, it's up to you, the user, to instruct MongoDB to build it. It will not build it for you if you don't ask for it. So the idea then is that if you don't have any index and you look up secondary fields, MongoDB will be obligated to kind of read the entire collection on disk. That's going to be very consuming. It's actually just like Spark, actually. So it's going to be slower. If, however, MongoDB realizes that it can use an index, even partially, then it's not going to read everything from disk. It's going to actually make use of the index to isolate the subpart of the collection that it needs to read, and it will only read from disk the parts of the collection that the index pointed to. So that means that what you load in memory is not everything, it's just a subpart of it. And then you might do more filtering in memory, but you know that's already less than having to go through the entire collection. This is why we have indices. The goal of an index is to read less from disk than you would have without an index. Here are a few examples. If I want to create an index that is a hash index on a field last that is within a field name, that's the dot, right? Then I say, okay, name.last hash, and then I can look up, for example, name.last Einstein. In that case, that's instant. It's going to use my hash index right there that I constructed before. Of course, it might have taken an hour to build, right? But when it's built, it's built. And then my query is almost instant. Here's another one. I might have an index on profession that is a hash index. Means that whenever I query for a specific value for the profession, not an interval, right? Specific value, then that's instant. Look at this query here. It's asking for the 2 filters, first on the profession and second on the theories. MongoDB is able to accelerate that query. How? it notices that here you're asking for profession physicist in addition to the other criterion. So it's already going to be able to use that index to only read from disk the profession physicist, all of them. And then in memory, it's going to filter more. And then in those that it read from disk, look for relativity. So this is why I have these two icons here. Here, it's efficiently read from disk only the physicist. And here it's filtered in memory after reading from disk, because that's not part of the index theories. Here's another one. I have a B+3 index. I'm also able to build B+3 indices on several keys. How do I do that? It's just the lexicographic order. It means that if I sort by birth and death, if I have twice the same birth, within these two, I'm going to sort by death. This is something you have in Excel too. If in Excel you try to sort multiple columns, that's going to work nicely. All right. So, and the 1 and -1, again, that's part of the low level of MongoDB. 1 is ascending and -1 is descending. So here I basically have a big tree where my nodes are sorted first by birth and then by death in ascending. So now, if I have a query that says I want this birth and that death, that's logarithmic. I'm just going to go down that tree and look up for the birth and then the death and then get my objects. All right? If I say -1, for the same birth, it's going to be ordered by decreasing date of death, right? But here it's a point query anyway, it doesn't change much. Okay, here's another example. A range, so the 1 means a tree index in ascending order of the key. So the birth is ascending. And here I'm asking for the births that are greater than or equal to 1946. So I'm just going to locate 1946 in the index and take everything that's on the right of that. That gives me my results. If in my query, I not only ask for a birth that is at least 1946, but I also ask for a death, it's as before. That part uses the index. So I'm going to load into memory everything that's on the right of 1946 in the index. What's on the left, I don't even bother to read it. Then it's in memory. And then I filter in memory for the death. Right. Okay. Now, there is some trivia fact or fun facts to know. If you order by birth and then by death, but the query only asks for the birth, you can also use that index. The reason is that if you have the birth and death, all of the ones with the same birth will be together. So if I want to locate all of the ones with birth 1887, it's like an interval for birth date, right? It's basically the interval between born in 1887 and dead in 1887 on the left-hand side of the interval, and the right-hand side of the interval is born in 1887 and dead in 2022 or later, right? Okay, well, I don't think anybody actually lives for that long, but you get the idea, right? Okay, this also works. With this index here, you can also make that query work. You just ignore the death in that case. This doesn't work. Does anybody see why, if you have an index that is a tree that's sourced first by birth and then by death, if you query specifically for a specific death here, you will not find anybody. Oh, sorry, you will not efficiently find. Can anybody tell me why? Yes? Exactly. You need to go through all the possible births. That's going to be very inefficient. You will have to check like 1,000 of them if your database have multiple centuries. So this is why this index here is totally useless for that query. You must start top down in your query. You have birth or birth and death, but not death alone. Right? Okay. The take-home message here is that if you build an index, let's say on these 3 fields, virtually, it's as if you also had an index on the first one or on the first 2 because of the remark that you had, but not if you start at the bottom, it doesn't work, right? So there are people that make that mistake in MongoDB very often. They create their indices and they will create that index, end that index, ends that index, but they do not notice that their indices are useless because since you have this one, you no longer need these two because they are already implied by the first one. So you can save a lot of space by having that in mind, that you don't need to create too many indices because it takes space, right, to have an index. All right. That's actually the last slide of MongoDB. Yes, go ahead. You have a question? Okay, so your question is about the storage. How do you store the index on disk and the real data on disk, right? You were asking, like, if you have an index, do you also reorganize the data according to this index? The answer is no. The answer is that the index is an additional structure. If you add an index, that doesn't touch the original data. So the original data is still stored in the way that it is. So the index just has a pointer to the data. It's really, you could call it an, sorry? It depends how you implement it. So there is, of course, a bit of extra work because you need to first look up the index and then look up the actual data. Yes, absolutely. So basically, the takeaway here is it's not trivial. It's not trivial at all, and this is why, I mean, this is a job, right? There are people who work full time as database architects. It is absolutely not trivial to get this correctly. For the scope of this lecture, we really do not need to get into this level of details for the indices. The main thing to remember is really that the index is an additional auxiliary structure that accelerates looking up the data in the database. Right, that's pretty much what it does. The way it works then when you actually store the data is that the data is also read in blocks. So if your index tells you to load a specific record, you will actually load the entire block that has the record from the original data. And of course, yes, that has the consequences that you say, that you might be unlucky and load more than you should. Yeah. It's a very complex problem, and it's an open-ended problem, right? It's never going to be solved. You can always find tricks in order to improve, but it's never over. All right, any other questions? No questions on Zoom? We have other questions on Zoom?
No.
No questions? Okay, should we just stop the lecture here on MongoDB, I assume? So just to summarize, what are the takeaways of MongoDB? MongoDB is kind of hybrid between Spark and PostgreSQL. Just like PostgreSQL, you can import data, update data, edit data, delete data, and so on very efficiently. Just like PostgreSQL, you have indices that make it fast to retrieve data. Just like PostgreSQL, it has a proprietary format on disk, which gives control over the way you store it. But unlike MongoDB, the data doesn't need a schema. The data doesn't need to be tables. The data doesn't need to be highly structured. The data can be actually a mess, just like you would have it in Spark. Right? So this is a compromise. However, the query language is not high level, and for a data scientist, if you sit in Jupyter notebooks, that can very quickly become very cumbersome to query data in that format, which will bring us to the next lecture. All right, so I'll see you on the other side. Load the slides. Thank you.